characterization, and modeling of asphalt material as one of the widely used construction materials in transportation infrastructures. And we hope this lecture series help students and researchers to make up ideas and to arouse, in fact, their scientific curiosity for their future research works. And today's session, which is the last session of this lecture series, is the topic is about the mechanism of moisture damage in asphalt. And our speaker and presenter is indeed one of the global expert leaders and pioneers of sustainability and resilience of construction materials, Dr. Ellie Fini, which is now as associate professor at Arizona State University. And she's also serving as an invention ambassador at the American Association for the Advancement of Science, a Fulbright Scholar of Aalborg University of Denmark, a senior sustainability scientist at the Global Institute of Sustainability and Innovation, and director of the Innovation Network for Materials, Methods, and Management. And her research mainly focused on the production, characterization, and atomistic modeling of sustainable novel materials for use in construction. Having published over 200 papers and being invited for as a speaker for different platforms, events, conferences. Her research also has been featured by BBC Women in STEM, Science Nation, Wired Magazine, and CNBC. And she's currently also the editor of the ASC Journal of Materials in Civil Engineering, and the top journal of resources, conservation, and recycling. And also, she has served as the president of ASC North Carolina Northern Branch and a program director of the National Science Foundation. And in recognition of her dedication and her achievements during her research career, she has also got many awards, including the NSF Career Award and many other awards, as you can see on the presentation. So we really appreciate and thanks Dr. Ellie Fini for accepting our invitation to speak for us about her research work. And before I pass on to Dr. Fini, I would like to ask everyone, please type and send your question during the presentation. As you can see in the chat in the toolbox at the bottom of your meeting window, the chat toolbox, you can tap it, and please send it to me directly. At the end of the presentation, I will, after I collected all questions, I will read them, and Dr. Fini will respond to us. And with that, I will welcome Dr. Fini and for starting her presentation. Thank you, Dr. Fini. Yeah. Dr. Fini? Yeah.
Do you see my slide? Do you see the slides?
No, not yet. Yeah.
What about now?
Yes, I think still no, but yes. Now we can see. Yeah.
All right. Very good. Hello, everyone, wherever you are. Thank you for joining for this lecture and seminar. I assume some of you at least been in the previous two lectures. So we talked last time, you remember, about aging and rejuvenation. So I want to tell you a bit about moisture damage, but you have to think about moisture is one of the environmental stressors. And much like anything else that happens to asphalt, when you see this piece of road sitting outside under rain and UV and air and all the other environmental stressor, moisture is one of those. So as the asphalt sitting out there and getting aged, moisture can happen and rain can happen from underground water or from precipitation. regardless of where the moisture comes from, that could affect your asphalt differently at different stage of aging. So brand new asphalt could respond to moisture in a different way than a very old asphalt. So I want to tell you about how the moisture and asphalt, they interact. These are two elements, right? You think about your asphalt, your bitumen, and now water is being exposed to it. So what would happen? Before we talk about how asphalt reacts to various environmental stressors, so I want to go a bit back to make you think about what you have in this piece of road. So when you actually look at the black road that I just showed you, it's made of this, right? It's a bunch of aggregates bound together with a glue, which is asphalt. So the black stuff over there, you see these tiny black windows, those are bitumen. And this bigger chunk of gray, they are aggregate, stone. Whether it's limestone or granite, that's your skeleton for your pavement, and then the binder is the glue that keeps them together. So when you think about environmental stressor, whether it's aging, UV, solar radiation, moisture, they attack each of these elements separately. You can think about how minerals like limestone or granite react to this environmental stressor, and how your bitumen will react. So speaking of reaction, you may have heard about a smart material. Initially, when you think about the smart, you always think about, I guess, sensors and somehow, a smart home and having devices. That's one way. Now, another way is your material actually responding to you. So if you actually apply certain stressor, if the material can react and respond in a proper way, that material is sort of smart because it knows how to behave, right? How to react. So I here sort of put the category into two. We have a smart and we have functional. So I'm going to tell you more about functional. So smart in this definition is basically react to external stimuli. If it's environmental or traffic load, it reacts. So when the material age, that means it reacts. When the material crack, that means it reacts to load. When it gets damaged due to moisture, that means it reacted with the moisture that was exposed. So another category is functional, when the material counteract the external stimuli. For instance, it can manage to resist oxidation. It can have some built-in reinforcement mechanism that can resist oxidation. It can resist cracking. For instance, if you actually put some built-in reinforcement mechanism that release stress properly and in a timely manner, so it can prevent cracking, because literally crack happens when the stress or the load you apply overcome the strengths that the material has. So it cracks to release that stress you applied. Or we have resistance to moisture, when the material can have some built-in mechanism to passivate or kick the water away instead of letting the water damage its integrity. So I'm talking about functional material. Of course, this lecture will be mostly focused on moisture as the material, how the material can be functional in terms of moisture damage. Obviously, none of us likes moisture damage. None of us likes asphalt to get oxidized and crack. Those are things that we have been studying and researching to prevent. So if you can actually build resistant mechanism against oxidation, against cracking, against moisture, that's a good thing. So here we talk about building resistant mechanism. Before that, I need to know what do I have in asphalt. So I'm going to tell you a bit about chemistry. I'm not going to go too much into it, but this paper here, I put it as a reference. You can check it out if you are interested to learn more about the chemistry of bitumen. So that black binder that I just showed you in the first picture is basically made out of molecules, and molecules are categorized or grouped together under these names as asphaltene, as maltane. So asphaltene is literally a group of molecules. It's not a single molecule like you talk about water being hydrogen and oxygen, H2O. Asphaltene is not one single molecule. It's a group of molecules. Maltane is another group of molecules. So why I'm telling you about group of molecules, not single molecule, because asphalt has a lot of molecules. It's almost impossible to identify and name each and every one of them. So we group them based on their solubility. When you actually dissolve asphalt binder in different solvent, you can determine their solubility. And in this class of material classification, we use solvents like N-heptane to separate asphaltene from everything else. So literally, things that are not soluble in N-heptane will become asphaltene. And things that are soluble become maltane. The polarity of each of these components are different. I put them here in the sort of a ranking order. You can see that asphaltene has the highest polarity, followed by resin, aromatics, and saturates. So asphaltene, as I mentioned, is the group that is not soluble in N-heptane. The rest is all maltane, and maltane itself can be separated into resin, aromatics, and saturates. So if we see the polarity of them being different, what it tells us is many things. One of the things that it tells us is they actually react to environmental stressors like free radical oxidation, like moisture, differently. So asphaltene being more polar is more prone to oxidation compared to saturate, which is less polar. So that at least gives us a sense of what material I'm dealing with and how we can build our resistance mechanism. I'm going to show you some reaction. Like I mentioned, this material is functional. It reacts to different environmental stressors. We talk about aging and oxidation is one of the environmental stressors. Here I'm showing you this figure just to tell you how material actually react differently. You can see asphaltene on the top figure and the whole binder, which itself has asphaltene in it, right? I mentioned asphalt itself is made out of asphaltene plus maltane. So when you look at asphaltene aging over time, it has this graph on the top. When we go from unaged to 2 PAV to 3 PAV to 5 PAV, and the vertical axis here is UV-V's absorption ratio. So asphaltene changed differently than the total binder. Why it matters? Well, in most studies, we always look at how the entire asphalt age, not each of their components. But here I'm showing you that asphaltene, which is one component of the entire asphalt, it actually ages differently. But we usually take the average of the whole sample. We just look at the binder as a whole. And in the table here, you can see how the saturate, aromatic, resin, and asphaltene, which together make asphalt binder, change over aging period. For instance, on the top, you can see saturate, the changes that is happening in saturate versus asphaltene, which actually goes from 19 to 29, while, for instance, aromatics goes from 19 to 7. So the change of them are different because they have different reactivity to oxidation. So as we talk about reaction to environmental stressor, that's one, right? Oxygen coming to attack your asphalt. We have other environmental stressor, including traffic load. When you actually have your asphalt and apply load to it, it reacts, right? So if you think about, I'm sure all of you have dealt with asphalt, but if you haven't, think about honey, how when you push your finger on top of the surface, it reacts, it change, it deform, and maybe it come back or maybe it doesn't, but reaction to that load you apply is another reaction. So in this case, you can see red, green, and black, they are force platform versus indentation. So sort of in the macro level, we use this nano indenter, but in a micro level, this picture, it shows that. But in an analogy, as an analogy, you can think of the honey that you are pushing with your finger, or a piece of asphalt, when asphalt binder, when you push it with your finger. So you have the force versus indentation, and you can see that the profile is very different for these three. Why they are different? Because this is the same asphalt, but it's been under UV for different period of time. So when there is 20 hours of UV exposure, you have the black. You have 50 hours of UV exposure, you have the red, and then at 100 hours, you have the green. So this material reacts to load, but differently depending on what stage of aging or exposure to environmental factor it has been under. If it has been under environmental stressor for 20 hours, you can see the reaction is very different if it has been under environmental stressor for 50 or 100 hours. So as your material is being exposed to this outside external stimuli, they are constantly reacting to them, and their profile is changing. So when you think about moisture damage as another factor, you cannot study it in isolation because you always have multiple factors combined. And aside from that, as the material sits out there and being bombarded by solar and water and wind and this and that and load, it gets changed as it sits out there. In this case, it gets actually thinner because some of the material that it gets aged or evaporate become sort of volatile and leave. So your material is actually thinning or getting thinner and thinner. In this case, I'm showing you the UV aging time and the thickness of the film of bitumen. Just sitting out there under UV exposure, the film thickness was keep shrinking from almost 600 to almost 200 nanometer. So as the thickness is shrinking, it is reacting, but one form of reaction is also loss of molecules, loss of material, which leads to thinning effect. And you can see these pictures and how it changed to become like this spot at the 400 hours. So the material is constantly changing as it's being reacting to external factor. So what I want to show you here is actually, when you think about the initial picture I showed you, you always have minerals, for instance, quartz or granite or limestone bonded together with bitumen, which is your glue. So if you think about this substrate, here I put silica as a representative for quartz, for instance. And you can see the bitumen on the top. So this is the molecules of fresh asphalt on the left attached to the silica on the bottom. And as the oxidation happens, it's sitting out there under sun, it oxidizes and changes. This is the oxidized version. So here we are comparing as the material sitting out there and getting aged, what happens to their interaction with the mineral. Interesting enough, when your asphalt becomes more oxidized and more polar, its interaction with silica becomes stronger and stronger. It could be a good thing from one side, but you have to consider everything at the same time. So yes, it is becoming bonded stronger, but remember, it is also becoming thinner. So thinner, but also stronger. And that's maybe a reason when you actually recycle asphalt, you get all these black rocks that have a very thin layer of asphalt completely coating the surface. Over time, they actually bonded pretty well as they oxidize. So here we show the oxidation, oxidized asphalt tin adhere or bond better to the surface of minerals. In this case, silica-based mineral, like quartz. And then we run another test with in this paper. I'm not going to go too much into detail, but you can check that paper for more detail. So we actually looked at the interface between silica and bitumen. Initially, when you actually shear the sample, this test is a viscosity test, but called MISTI, moisture-induced shear thinning test, which basically measure how the two materials bond together under shear. So in the case of fresh asphalt on the top, no aging, and then you have the oxidized version on the bottom, severely oxidized actually. You can see when you shear them relative to each other, stone and bitumen, they shear very differently. The fresh one shear right away, very easy. The oxidized one has a much steeper slope, and the higher the slope in this case, it shows higher bonding between the two. So here we could differentiate between fresh and oxidized asphalt, how they interact with substrate, in this case, silica. So now that we know as the material sits out there, their behavior and reaction to environmental stressors like moisture varies, we understand that we have to look at them under different conditions. We cannot just look at the fresh asphalt and decide what would happen in terms of moisture damage, because as it age and change and become thinner and more polar, the phenomena completely change. In this case, is another test that can actually study moisture. When you have, you literally want to see how the two materials like each other. In this case, you place a droplet of bitumen on top of your substrate, which could be glass, silica, quartz, any substrate that you want to study underneath, and a droplet of bitumen on top. Ideally, the two materials could flatten and wet each other. So here, dry sample on the top, it shows that the angle is 7 degrees to 12 degrees, very little, because bitumen literally flow over the aggregate. Then we take this sample and put it in water and wait and look at it. So with this camera, we can keep watching the sample as it changes due to water exposure. So here you can see 4 different bitumen having different modifiers and how they bead up. The initial angle for all of them is 7 to 12 degrees. As we watch each of them, they start beading up within the same time period under the same condition. The first bitumen bead up to 63. The second one on the bottom bead up to 132. The third one to 124, and fourth one to 140. So you can see right here that, and all of them have same substrate underneath, same exact substrate. So as they bead up, sort of they are running away from substrate, replaced with water. That shows their affinity towards substrate is lower and lower. For instance, the one that beats up to 63, well, still likes the substrate. The one that beats up to 140 is completely running away. It doesn't even want to stay there. So if I just look at this and want to decide which one of these samples of binder will be more susceptible to moisture, I would say the last one, because it beats up so quickly. Does it mean that second or third would be okay? It depends on the conditions. But if you're ranking all these 4, the first one which beats to 63 will be the best one. Then you have the 124, the second best, 132 is the third best, and 140 is the worst case. So we can rank bitumens based on their susceptibility to moisture. So, having said that, consider that there would be other environmental factors that could change the picture. But if you're just looking at how these 4 bitumen behave when they are exposed to water, you can rank them with this test, and it's pretty repeatable. So the information for that test also can be found in this reference right there. So when I'm showing you different test methods to evaluate moisture susceptibility of the bitumen. But then even if you know that the bitumen is moisture susceptible and it's gonna have problem down the road, what would you do? Because we as engineer, we don't just look at the problem, we always look for solution. So I'm gonna tell you a bit more on why we do care and what can we do about it. So first of all, moisture damage is a major problem in asphalt pavement degradation. When the moisture starts degrading your bitumen and separating it from your binder, literally your glue is gone. When the glue or the binder is not keeping the stone together, then the whole asphalt falls apart. So moisture damage actually can lead to crack, pothole, rotting, and many other down the road damages, because you basically lose the integrity of the entire asphalt when the glue is gone or separated from the substrate. So in the US, most of the states here, 41 of them reported that they do have observed moisture damage, and many of them use counteracting measure, which I'll tell you about in a minute. And it caused a lot of course, cost, because that's a damage. And this significant cost involved with this prevention could be, I guess, avoided if we look at the moisture damage priorly before we even start the design. So this is just an example of how moisture damage could exacerbate and make the whole thing fall apart. One of the tests that most of you are probably familiar with is tensile strength ratio, where we actually make a sample of entire mixture, aggregates and binder together, a sample of superpave, for instance, we use here in the US, superpave specification, and we make the TSR sample, a cylindrical sample, and condition it in water. Before and after conditioning in water, we measure tensile strengths. The ratio between the wet and dry strengths will give us the ratio. So that ratio, which is basically wet strength to dry strength, is supposed to be above 80% in most states, specification. If it's too low, that means you're losing a lot of strength. So literally, when I'm telling you ratio, when you divide the strengths at wet scenario to dry scenario, the best scenario, if it doesn't change at all, you're gonna get 100. If the strength, regardless of putting it in water, is the same, that means dry strength and wet strength are the same, then I'm gonna get 100%. So that nearly never happens. So anything above 80 is still considered good. But regardless of what the spec says, here I'm showing you a bunch of additives that are added to asphalt. In the case of control, we just got a ratio of 67%. And then it started, which is bad. So we started adding different additives to see how they behave. And in one scenario, when we had amine-based additive, we got 85%. And some of the biomodifiers we used, or zeolite or wax, showed different numbers here. So there has been a lot of study on anti-moisture damage, anti-stripping, liquid anti-stripping, which are mostly amine-based. There are a lot of study on silane-based anti-stripping, all to help with TSR and moisture damage. So TSR being a strength test, sometimes it actually gets you even a higher ratio for your wet compared to dry, which depends on the additive and modifier you're using. For instance, if you're using lime or cement in some scenario, you may actually get a pretty good TSR ratio. There are some controversy on the results and what represent as moisture damage, but that's the most common test that is being used for this specification. Some states, they also apply a freeze and thaw to exacerbate or accelerate the damage within the period they are testing in the lab. Some, they don't require freeze and thaw. So overall, you can see this test is another measure of change due to water. So as I mentioned, because it's about change, we actually don't want our material to change. We want it to stay resistant and resist any change. Literally, if we have a material that does not change due to water conditioning, then you're gonna get a 100% TSR. Another test is Hamburg rod tester or moisture. In the case of Hamburg rod tester, we can also study moisture using the inflection point, which is basically this number of cycle. You can read the cycle here where the inflection happens. So as you identify the inflection, you can read the cycle corresponding to that to see if the material is showing moisture damage too early. If the material doesn't show any inflection, then there is no concern with the moisture damage. But there is different spec on how many cycles would be considered as acceptable. So in this case, also we can see different additive show different inflection, some earlier, some later. Another test which can differentiate in terms of moisture test. So you can see at the binder level, I showed you some tests like that simple contact angle, looking at how it beads up, and here at the mixture level. Either way, if you detect the problem, the sooner, obviously, the better. So you can then have a counteracting measure. But regardless of detecting, that's not a cure. That's not the problem will not go away if you detect it. You need to figure out how to actually avoid the problem. Another test that has become also common is bitumen bond test, when they look at the bonding of a piece of bitumen on a surface of a substrate, and they pull it in away from the substrate. They measure the load that requires to pull the bitumen away, and they measure also the area that is detached or it's cohesively failed. So in this case, you can see the neat sample, for instance, is almost peeled away. The one that had some additive peeled away less, more or less cohesively broke. And you can see here the peak load at different scenarios. While the strengths here, for instance, at the first case is neat, dry, you can see it's 250, and the wet here actually become around 270. You might think, well, the water actually helped, right? The wet is better. Well, not necessarily, because actually when you have to look at the mode of failure. That's the first thing. And second could be that the water promotes some sort of oxidation, early oxidation in your material, depending on what material you have. So ideally, we do not want change as a result of water conditioning. Whether it's increase or decrease is still undesirable because it's considered a change. So speaking of a test that can truly measure changes at the interface. Many people have used surface energy approach, and there's a scientific way to look at how energy of the surface change with or without presence of water. And then you can calculate work of adhesion as a result of this calculation. In this case, we measure surface energy of bitumen, and then separately surface energy of stone. And then we calculate work of adhesion. And then we do the same thing in wet and dry condition to calculate a ratio, which will be referred to as moisture susceptibility index. In this case, you can see the index is also changing. For the neat, you have around 4, while the one that has 10% of this additive with alphabetic name, or these are not actual material name because it's basically names are blinded. You can see that 10% of WVO, you can see that CAMC is 2-3 times higher, from 4 to 12. So when you add a material, surface energy will change, because sometimes you add an additive that is polar, sometimes it's non-polar, and it changed the whole surface energy. In the case of WB, you can see that CAMC actually dropped to 1/4, from 4 to almost 1. So what are we measuring in case of surface energy? Are we measuring bitumen air interface, or bitumen stone interface. So when you are actually talking about the asphalt that is bonding bitumen and stone, you want the interface between bitumen and stone, not the bitumen and air. Most of the tests that we use, including the Wilhelmi plate or surface energy approach, we measure surface energy of each one of them separately in air and then calculate work of adhesion as a result. The question is, bitumen air interface is not the same as bitumen stone interface, because bitumen has polar molecules, as I showed you before, and they move around. Sort of like, think about it as a magnet. If the molecules of bitumen are moving, the polar one will go where the polar substrate is. And non-polar one will go where the air is, because air is non-polar. So if it goes toward air, there are molecules that are non-polar. What goes toward stone are the molecules that are more polar. So right there, you have a different interface. And it could be erroneous if you actually use air interface data to calculate what will happen at the stone interface. I'm going to show you that difference with actually measurement to tell you what is on the air surface of bitumen is different from what is on the stone interface. This one is atomic force microscopy. If you're not familiar with it, don't worry. It's basically an indenter cantilever passing over your sample and tiny touches of your sample, if it's contact mode, or we do have non-contact mode as well. And then it plots you this morphology right here. So based on this morphology, you can see katana phase, and this also referred in different literature as bee structures, because they represent look like bumblebees. So you can see here different structure on the surface of bitumen. When we touch with the cantilever on the surface, we plotted this. And then as we want to see, okay, if the same properties happen at the interface, we invented or sort of come up with this method. You can check in this paper if you're interested, to look at the interface. I already saw the surface, the air, and that's the picture on the top. All those bumblebees are shown on the top. But I want to see what's at the interface. So what we did, we made this sandwich of two substrates, up and bottom, upper part and the bottom part, and then bitumen is sandwiched in between. Then we break the interface and we look at the cut between glass and bitumen. So right at the broken interface, right here, you can see the broken shards. We look at those and we saw this image. So the sample on the surface up here on the top, the sample at the interface is the bottom part. They are very different because, as we expected, the material that moves toward the surface is different from molecules that moves toward the interface of the stone, or in this case, glass. So there is a difference between surface and interface of the stone. And the overall conclusion here, the surface is not telling you the whole truth. It doesn't give you the whole picture because it depends on what is at the surface. Is the air at the surface? Is the stone at the surface? And what type of even a stone? Is it granite at the surface, or you're talking about limestone being on the contact surface with bitumen? So those could change the picture. I told you all of those because when the water actually comes in and want to get in between bitumen and stone, it's important what water sees right there because it's attacking your interface. It's important for us to know what is the molecules that is at the interface that the water will attack. So effect of water on the surface here and the bulk and the interface with the stone are also different. You can see the effect of water on the surface. We had these bumblebees that I showed you in this picture on the top right here, and then dump water on it. We put water 0 day and then keep looking at it 1 hour later, and we went all the way to 24 hours. Keep looking at it, how it changed the surface, just the surface. And you can see this appearance of the dots on the bitumen surface as the time lapse. Effect of water exposure on the bitumen surface was very interesting because it also confirmed our hypothesis that the polar molecules will come to the surface and non-polar one will run away from the polar surface. So if you actually put a thick sample like this, a thick bitumen, and do the cantilever test, the AFM test, at different depths, and each picture, it shows where it's touching. So in the thick layer, it sees the surface like this. As we get further away from the thickness and gets to the glass, the substrate, the shape changed to the one on the right. You can see that interface closer to the substrate does not look the same as what we see on the surface. So that was important because when the water comes in, the water wants to get between the black and the gray, literally want to replace the bitumen. So it will get to the interface that is closer to the bitumen and glass surface, and what it sees is actually this structure on the right. So if water sees this and it starts cutting the bitumen away from the substrate, then that's right there, you have moisture damage. So now that we understand what type of structure, what type of molecule we have at the interface, maybe we can control and prepare some built-in mechanism, reinforcement mechanism, to avoid the damage. In this case, you can see actually the molecules that we added as the reinforcement mechanism to go to the interface. And in the case on the right, there is no built-in mechanism. We did not do any counteracting measure. And you can see the asphalt and the substrate are actually separating when the water comes. And this was actually very susceptible to moisture. When I showed you this, the control sample, TSR was pretty bad. That's the same sample. So the molecules actually go away when the water comes. But in the case of amine, amide doped sample, we just added molecules of amide, and you can see this layer formed right at the interface of silica, which is relatively more resistant to water. So instead of typical asphalt molecules sitting at the interface, now we created a bridge right here at the interface, which will resist the moisture intrusion. We looked at it at the molecular level when we added the amide molecules. That's what happens. The head of the amide actually interact with the silica. You can see this at the head, and the tail interact with asphalt. So right there we have a bridge which sort of work to keep the whole thing together. When the water tries to attack, this bridge will resist much better than no bridge, which is the control sample. So in this case, we actually measured the adhesion, and in the case of control, the molecular binding was 1,386. We had the amide doped, and it became double. So the interaction using those amide doped was much more, twice as more as the control. And then we wanted to test that, go back to this test, which I showed you, and check the results. So the control was the sample that got to 140. When we added amide molecules, which is this BB molecule, we got 63. So the same control sample up here, when we added different modifier, had different effect. And this modifier was amide, which then we did the molecular analysis here to see what happened. So when we added amide here, the mechanism shows as a bridging mechanism. And here we got to 63, while others, they were much higher. So with that, because we understand what's happening at the water attack is at the interface, we can build a resistance mechanism right there at the interface. But how can I tell a molecule to go to the interface when I add it to binder? I can't just tell, like, dictate it to it. We have to make sure that molecule has preferential adsorption toward the substrate. So it can migrate to the substrate on its own when we add it to the bitumen. Otherwise, we can't go one by one and put them at the interface. So here, one mechanism was to build a resistance mechanism by adding amide molecules to go to the interface right there and create a bridge. In another scenario, we added polyphosphoric acid. These are the red sample. Polyphosphoric acid goes to the silica surface as well, as you can see here. It's actually pretty active to go to the interface. But polyphosphoric acid itself is moisture susceptible. So now you do have a bridge, good, but your bridge itself is moisture susceptible, so it's not helping down the road. So we have right now two problems in hand. One is to get molecules that make that bridge. Second, make the bridge be strong and moisture susceptible. So I wanted to tell you about the bridge mechanism because the molecule we added as amide is not the only one. There could be other bridging mechanism that could work as well. And this is open research, there are room to do a lot more. But one thing, if you get into this area, make sure you don't add a modifier like here, I just showed you. Polyphosphoric acid worked beautiful. It goes to the interface and makes the bridge. But when the water comes, polyphosphoric acid breaks down itself, and now you don't have as good of a bridge anymore. So make sure you consider both factors. One other thing that I haven't gone through too much and is in this paper, you may want to check it out, is what if the molecules that are in the bitumen, and they actually, if I don't add anything, some of the molecules of bitumen will go to the interface because some are more polar, some are less polar. What if I arrest the bad molecules so they cannot go to the interface? Because if they go to the interface and they make that bridge and the water comes and those molecules are moisture susceptible, then I'm actually in a worst case scenario, right? Just like what PPA does here. It goes to the interface and then it breaks when the water comes. So this paper is talking about using active minerals as arresting mechanism for acidic compounds of bitumen. Most of those acidic compounds work as a bridge, which is actually soluble. So you do have a bridge, but the bridge actually is soluble. So you don't want those such bad bridge. We can arrest them with other, like mineral, in this case, active mineral fillers, so they don't even get to the interface to cause the damage down the road. So two mechanisms right here you learned. One is have active good molecules that make the bridge and they are resistant. That's great. The other one is get rid of the molecules that are not helping and actually can hurt. So if you get rid of the molecule that hurt, then they're not there to damage, cause or promote or accelerate the damage. The second way, let them be there, but make a better bridge with adding molecules that can make a strong bridge to begin with. So those problematic ones, they don't get a chance to make a bridge and then dissolve. So this one here is an example of adding amides that then they make good bridge, that they are not dissolvable. In this case is a bad bridge, which actually can dissolve. So we are using some active minerals to arrest them. They don't get to the bridge. So then other molecules that are not as soluble, they have a chance to reach and make the bridge for you. So two separate mechanisms. If you have any question, I'll be happy to answer. And there are a bunch of papers on moisture damage, which are dealing much more with the chemistry side. I didn't want to go too much on the chemistry side, but if you have questions, I can talk about those as well. Back to you, Ali.
Okay, thank you so much. Thank you, so much, Dr. Fini, for really interesting, work. Really, as you said, in the molecular level, and discussing about the damage mechanism in asphalt, and it was really informative. So many, interesting things are we can see, we witness about how really damage can affect the and moisture can from the in the bitumen level, in the binder level, and then we go up to the mixture, until we go to mixture. So it's really very, very interesting stuff that you talk, and really appreciate it. Okay, so if among our presenters, if there is any question, if anyone has any question, please inbox, please write your question. I really appreciate it. So Dr. Fini will respond you. Any question still now? Okay. So it seems that no question from attendees. Actually, Dr. Finn, I have a question. It was really interesting. You talk about binder air interface and binder aggregate interface. So how about the binder interface and the moisture effect on it? I mean, we are talking now about the cohesion, in fact. So how about that? Is it something that we should be also worried about, concerned about that, besides the binder aggregate interface and the binder air interface? Yeah.
That's a very good question, Ali. Actually, if you look at the middle picture here, is a bit thicker. So the one on the first picture on the left is the top surface. And then you can see in the second circle is a bit thinner, but the last one is more at the glass surface. So even in the middle section, you have a different profile. On the top three figure, you can see the changes of profile. So yes, the moisture can, water can attack any part of the sample, any part of asphalt. But as you can imagine about when you have a chain, and if you pull it, it breaks at the weakest point. So if the weakest point here is the glass bitumen interface, the water will break that chain first, then damage the other portion of the bitumen. But cohesive failure and adhesive failure have been discussed as two forms of failure under moisture damage. So it is possible that some of the bitumen that they don't have very good cohesion, it actually breaks in cohesively, like in this scenario, when they pull it. In one scenario, you see more of an adhesive failure. Another one, you see more of a cohesive failure. So depending on your bitumen, it is possible that cohesive failure happens as well. And that's more or less when you have soluble or material within your bitumen bulk. Most of these tests are done on mastic level, which then you have mineral fillers, which could play as your weak point. Yeah. Good question.
Yeah, great, thank you. And okay, and even following this discussion, although you talk about also the moisture damage related test for evaluation for, and also at the mixture level. So this is what I want to know as a whole when we study this stuff. I mean, for example, the moisture damage related effects on the asphalt binder, and then we go to mastic level, and then we go to mortar level, and then we finally goes to up to mixture level, because they are all at the end this mixture we will have all together. So how we make sure, in different levels of this combination, we are moving in the right direction. I mean, when we want to, evaluate all this, for example, the moisture that you talked today about it. So how we want to know, so what's your, take on this? What's your opinion about this, that when we move forward, from binder level, go to mixture level, how we should take care of all of these things together?
Well, actually, when you think about mixture at different scale, when you go very, very small scale, you still have mineral fillers that are in contact with your bitumen. So if we think about moisture wanted to break the weakest chain, and in this case, if the mineral filler you're having interacting with bitumen, that's the first line of interaction. And that's not compatible, or the water can get into that interface, even if it's like just few micron size. That's where the damage initiates. You may actually see it in your TSR in a larger scale when the whole thing fall apart, but the initiation is where the weakest point is. So in overall, to answer to your question, if we are looking at a chemistry-driven moisture damage, which is separate from what is caused by pore pressure, there has been a lot of study on pore pressure as a cause of moisture damage, and how the structure of asphalt could promote pressure build-up and cause the mechanical damage. That's a comprehensive study of its own. I'm talking about chemistry-driven moisture damage, where you have molecules that cause weakness at the interface of the bitumen and substrate. In a very small scale, your substrate can actually be those mineral fillers, which are passing off 200. sieve 200. So very, very tiny mineral filler still, that's where the first point of contact with bitumen, where the filler get coated with bitumen. And if the filler bitumen interface has molecules that are soluble and they make bad bridges, the first crack or initiation of the crack will be right there at the interface of the bitumen and mineral filler. That whole thing, after you consider this chemistry-driven moisture damage, then you have to still look at other factors that contribute to moisture damage, like the structure of the mixture, pore pressure, and other mechanisms that cause such damages. As for the measurement, you can actually start measuring at the binder level, because you're talking about molecules that are susceptible to water. Just like I showed you, amide was working better than other molecules, for instance. These are molecules. So when you go look at it at the mixture level, that could give you an indication, but it's way larger than the scale of molecules. So any test that measure at the bitumen substrate interface could tell you if you have something that is susceptible or not, and that could be a good start.
Great, thank you so much. Yeah, okay, any other questions from attendees for this today presentation? Any other question? Okay, so it seems that there is no other question. So I have Dr. Fini, thank you. In this 3-session presentation, you introduce us with very very new topics and all kinds of topical subjects that now we are dealing with it, especially in terms of within the context of sustainability and resilience of construction materials. We talk about and discuss about the using end-of-life plastics in bitumen composite, and then using regenerators, and also for in the aged binder, and then today the mechanism of moisture damage in the asphalt binder. So I have two overall questions. The first is then, based on your expertise and the knowledge that you have, I would like to know what are the existing challenges or the current the problems or gaps that we are dealing with, or we couldn't solve it yet now, and is this our scientists, researchers are struggling with them. So this is one my question. And my second question, I would like to give us or provide us a overall image of the future road in this direction that you are working, and about especially in terms of sustainability and resilience. We really appreciate it if we can get some of your opinions about this. Thank you.
Well, regarding let me answer your second question first on the future of our direction of Asphalt and what research is needed. Right now we have a lot of computational power with the advancement of computational tools, and we could, before years ago, we had to, run one of these simulations, molecular simulation, probably wait for a few weeks to a month to get one answer, and now it's much faster. So with the advance of the computational power, we can do things that we were not able to do before. So that's one direction that asphalt and construction material as a whole is moving toward, to be more chemistry informed design, where you can actually diagnose and expect problems at the design level and address them right there when you are dealing with the bottom-up approach. So some of the work that we have done, and some of those I talked to you about, is using molecular understanding, molecular mechanism to tell you how to design. And I'm not talking about simulating or mimicking what is happening in the lab. I always tell my students, if I can measure something in the lab, we don't need to model it. We don't need to make a model for it. So we use the modeling to inform our engineering design, to understand what is the mechanism behind one observation. So with more and more advances in this field, with other folks in the computational science joining folks in asphalt and material to design novel and future material, this has become more and more, I guess, a norm. Still, we have a long way to go to be able to design and I don't want to say asphalt, because the future of roads may not necessarily be a petroleum-based asphalt. It could be a binder, a glue that keeps the skeleton together. So the future binder, future material used in construction could be very much designed and synthesized from a bottom-up approach, molecule by molecule, where you know the synthesis, where you know the structure, much like when you make a Lego. You have the Lego pieces of black and yellow and green and so forth. You put them together, you make a gadget. Similar approach could apply to our future pavements when everything is designed molecule by molecule and is informed by the performance. So this is what I'm seeing with all the machine learning tools that are coming with the data science and analytics, combining with material science and engineering, all for the benefit of built environment and pavements. As for specific gaps you asked about, I think right now, many of us are looking at sustainability as more or less a metrics for recycling. While it's a good thing, but recycling is not always the same, or it doesn't give you a full picture for sustainability. I'm actually an associate editor of RCR journal, which we talk about resource conservation and recycling. That's a good thing, but you still have to think about whether what you're recycling adds value, and whether what you're recycling itself is meaningful in terms of sustainability as it comes to carbon counting, energy that goes to its recycling, and so forth. So putting that aside, if recycling still is as it is a big deal, and we are all moving toward more and more recycled material in asphalt, which is a great thing, we need to think about how recycled material could be seen as upcycling. How can I actually look at a pile of wrap and look at it as a fresh material that I can reuse and upcycle rather than downcycle? which then it comes to the concept of rejuvenation, and can I revitalize to a point that this material is as good or maybe even better than where it started? That needs a lot of science and students and bright minds to come together and work on this topic. So recycling actually become upcycling at some point.
Great, great. Thank you. Wow, great. Thank you so much for giving us an outlook for the future and the existing problems and challenges that we face as a civil engineers, that we should also now being more taken care of, the sustainability and circular economy in construction materials for transportation infrastructure. Thank you so much, Dr. Fini, for this series lectures. We learn many things, and I would like, on behalf of School of Civil Engineering and Key Lab of Highway Engineering of Sichuan Province, appreciate you for accepting our invitation. And I know that although you are now on holidays and you have a busy schedule, but accepted our invitation, and it's an honor really that have you. And we're really looking forward to meeting you in the future in person, hopefully after this, travel and border restrictions, remove. Hope we can have you also in future, in person. So really thank you, and really appreciate you for accepting our invitation. Thank you so much, Dr. Fini.
Sure, Ali. Let a student who attended these talks know that if they have question or a specific need with their research, they can always reach either to you, and you can transfer it to me, or they can even directly reach to my email at efini@asu.edu.
Yeah, sure. Of course. Thank you so much. Yeah, really. And thank you everyone who accompany us during this 3 lecture series. Yeah, I hope everyone could learn something, and especially our student researchers make up ideas for their use future works, especially in terms of sustainability. Okay, and with that, I will wrap up today's presentation, and I wish everyone success and a very successful New Year to 2022 for everyone. And thank you so much, and have a good day, everybody. Have a good evening. Have a good afternoon, everyone. Bye-bye.